Hey everyone. So in this part, we are going to look at clustering methods that use statistical models. So this approach is very, very different from what we have been looking at so far. So here we will be assuming that our data in the different clusters are generated from different mechanisms. And these mechanisms are basically different statistical, different distributions. So a lot of advancements in clustering methods have been achieved by using this new approach or this different or this approach of statistical modeling. So we're first going to do a little bit of exploration into how data that is generated from different distribution looks like. So this will just give you a feel to this whole idea. So here I have x1, which is generated from random normal distribution with 500 points. Mean is -5 and variance is 1. x2, I've generated 500 points from random normal with mean 10 and variance 1. So you can see that I'm generating data from two different distributions. Both of these are normal, sure, but they have very, very different means. Now I can also generate data from say a normal and exponential or any other pair of distributions, okay? So this is just for demonstration. So in X, I combine both of these, all of these points. So now I have data which contains 1,000 points, 1,000 elements, out of which 500 are from one kind of distribution and 500 are from this other kind of distribution. So before I plot anything, I'm just going to shuffle the data, right? So what I have is all of the first 500 elements are from cluster 1, and here all of this 500 elements in x2 are from cluster 2. Now, if you do random sampling, you would imagine all of these are mixed up, right? So that's why I'm going to just shuffle this data set. So it's more representative of an actual random sample. So this is a histogram of y, which is basically the shuffled version of x. And I can see these two parts. Okay, so I have like one histogram, I have one part here and another part here. So if you ever plot a data set and if you see two parts like this, then you can be assured that the data is generated from two underlying or two different distributions. So this is just a different way of visualizing the data set. On the x-axis, I have observation number. So the first point would be 1, comma, its y value. So you can see that I have these two lines here. It makes sense that this is basically the first 500 observations that are centered around -5, and this is the remaining 500 observations that are centered around 10. So this is just another way to visualize the same thing. X-axis is just the IDs or the number or the observation number of the data points. This goes from 1 to 1,000 because I have up to 1,000 points here. So you can see that there are two clusters here, right? I mean, you know that there are two clusters, and because the points have been generated using two different mechanisms. But from this plot, you could easily be able to guess that there are two clusters. So this is a very different kind of different kind of a situation here. So in x1, I have again the random normal distribution, mean is 0, variance is 0.1. In x2, random normal, mean is 0, variance is 2. So again, these two are different distributions, right? Because variances are different. So let's shuffle the data and let's look at the histogram. So from here, if you just looked at the histogram, you cannot really say whether there is 1 or 2 or 3 underlying clusters, right? You cannot say. Then I'll look at this plot where I have the observation number on the x-axis and the actual observation value on the y-axis. I have this line here, right? So many points are clustered around here, and then there is the scattering, right? So you see a very different situation here. It's not obvious whether there is 1 or 2 clusters, right? We cannot tell it visually very well. So this is just kind of to give you an idea of how data coming from different distributions will look different. And this mechanism of clustering using statistical models should help us cluster these kinds of data. We'll see later on if we can actually play around with this a little bit later on, generate data from different distributions and see how the algorithm that we will learn here works. Like, I'm pretty sure that it will work very well for this data set, but I'm honestly not sure how well it's going to work on this one. Okay, so I don't know, but at the end of this class, probably maybe end of next week, we will revisit this example and see how this algorithm behaves on this. Okay, if you think about this, I know that k-means and hierarchical methods will not do very well to cluster this data set. That's I haven't tried it out, but that's what I think. Maybe you guys can generate data, this data, and see how the k-means and the hierarchical work on this. Okay, so before we get into the details, we just a little basic review of some probability stuff. So probability of A comma B is basically probability of A intersection B. So instead of intersections, you use comma. It just means the same thing though. So we'll take a look at the Bayes theorem. So Bayes theorem is this. Oops. So I'll just have my pen on in case I need it. So Bayes theorem is this. So it says that probability of A given B, this line means given. I'm sure most of you know this by now, but no harm in reminding. So probability of A given B, or A conditional on B, is probability of A and B, or the joint probability, divided by the probability of B alone. This is the Bayes theorem. This is the multiplicative rule. You can obtain the multiplicative rule from the Bayes theorem, right? So I'm just rewriting the Bayes theorem. So what does the multiplicative rule say? It says that probability of A and B, or probability of A and B, is probability of A given B times probability of B. You can of course easily write it as probability of B given A times probability of A as well. Okay, and then finally the third rule, I'm calling this as a splitting rule. This is a made up name. What does it say? It says that probability of any set A can be written as probability of A intersection B plus A intersection B complement. So I think these are the only three rules of probability, and these should be enough to understand most of the theory that follows. So the Bayes theorem, the multiplicative rule, and the splitting rule. So let's try to formalize our setup a little bit. Okay, so I'm going to assume that I have two clusters. So k is equal to 2. This variable c indicates that so c is equal to 1 means I'm talking about cluster 1. C is equal to 2 means I'm dealing with cluster 2. So cluster 1 contains proportion of a P1 proportion of items, and all of those items have this density F1. Cluster 2 contains P2 proportion of items, and all of them have this density F2. So coming back to our previous example of normal distribution, so cluster 1 contains items, 50% items, so P1 is 0.5, with density of normal with mean -5 and variance 1. Cluster 2 again contains 50% or 0.5 proportion of items from normal distribution with mean 10 and variance 1. I'm talking about the first normal example that we saw. And then so C is a variable. Probability that it takes value 1 is P1, right? Because P1 proportion of items are in cluster 1. Probability that it takes value 2 is P2, because P2 amount of items are in cluster 2. So this is the simplified setup, right, of this entire clustering problem. So I have two clusters, Cluster 1 has items with density F1. Cluster 2 have P2 proportion of items with density P2. So given an observation X, right, how do we write the density or the probability of this observation? So we know that if X is in cluster 1, it has density F1. In other words, I can say that F1 is the conditional density of X, given that it is in 1. So F1 is the density of X given that it is in cluster 1. So this is for all of those folks who have taken 310, you have studied conditional densities. Now, if you haven't, then you can just focus on this one line that if X is in cluster 1, it has density F1. If X is in cluster 2, then it has density F2 because that's our premise, right? That's our assumption. Or we can think of F2 as the conditional density of X given that it is in cluster 2. Probability of C we have already discussed. So to find the probability of X, what do we need, right? We have all of these ingredients and these are enough to find the probability of X. So let's see. So P of X, so the probability of X can be, this is a splitting rule that I'm using. So it can be written as X and that X is in cluster 1 plus probability of X and X is in cluster 2. So that's what I mean by X comma C is equal to 2. That means probability of X, and I'm assuming that X is in cluster 2. So this is the base theorem. This is the multiplicative rule. So multiplicative rule lets me write this. So X probability of X comma C is equal to 1 can be written as probability of X given C is equal to 1 times probability C is equal to 1. And you can again use the multiplicative rule on this part and get this expression. Now let's look at each of these terms, right? So probability that X given C is equal to 1, that means, so we know, right? So density of X, if X is in 1 is F1X. So this is just F1X. Probability that C is equal to 1 is P1. Probability that of X given it is in cluster 2 is just this density, right? So F2 of X times probability that C is equal to 2. So basically, now I'm going to call this sum as mixture distribution. So mixture, so basically X can either be in cluster 1 or cluster 2. We don't know. So this mixture density or the mixture distribution of X is basically density of cluster 1, F1X, times probability or the proportion of items that are in cluster 1 plus density of cluster 2 times the proportion of items that are in cluster 2. Okay, so this is how we derive mixture distributions. So this was just for a case of 2 clusters. So if we have more clusters, we can generalize this, right? So you see where the word mixture comes from. So I have 2 distributions. So X has this mixture distribution. So if there are k clusters, that means, so the ith cluster has this density function Fi, and it contains Pi proportion of observations. So the mixture distribution of a single observation X is given by this. So either X is in class. So basically, this is extending the previous argument to k cases. So it'll either be in cluster 1. So in that case, it has density F1 times probability P1, or it's in cluster 2. So F2 times probability P2, and so on. It can either be in cluster K, so we get Fk times probability or times Pk. Okay, so this is a mixture distribution. So the most common model for this is a multivariate normal. So mostly people will assume that these FKs, right, these densities come from multivariate normal distributions. Why multivariate? Because your items can be can have multiple dimensions. If they're one dimensional, then you'll assume that you'll just assume regular normal distributions. But this is a multivariate class, so we'll assume multivariate normal distribution. I'll talk more about this in my next video. So this is a mixture distributions, okay? One thing I think I forgot to mention here is sum of all the pKs, right, has to be equal to 1. So sum of all of these proportions has to be equal to 1. So cluster allocation. So how do we use this to actually allocate this observation X to some cluster? So for now, assume we know this K. We know the total number of clusters. I think this should have been small k. So we know all of these densities, right? So we know that, so in our example, we know that the first density is normal distribution. We know exactly that the mean is -5 and the variance is 1. For F2, we know exactly that the mean is 10 and the variance is 1, right? So we know everything about these distributions. We also know these proportions. So if we know all of these things, let me just write here a small k to indicate it's possible I might have switched between small k and capital K, but most of the k's just stand for the total number of clusters. So yeah, so we pick an observation X. Which cluster should we assign it to, right? What do we do with all of these probabilities? So C is a random variable. It takes values from 1 to k now. So this basically reflects the cluster of choice. So probability distribution of this C is this. The probability that C is equal to I is just Pi, right? Pi is the proportion of items that are in the ith cluster. So in step 1, we will calculate all of these conditional probabilities. So this is the probability that C is equal to 1 given X and so on till C is equal to K given X. Then we will see which of these numbers is the maximum. So if for some particular I, so if probability C is equal to I is maximum, then we will assign X to this ith cluster, right? So step 1, calculate these conditional probabilities. Step 2, see which is the maximum and then make the allocation. Okay, so how do we calculate these probabilities? So in order to keep things simple and intuitive and understandable, I have indulged in a heavy abuse of notation. If you've taken a probability class, you might notice this, but I just want to make sure that everyone understands the spirit of things here, okay? So I'm not doing rigorous proofs, but I just want to make sure that everyone gets an intuition behind the mathematical concepts. So probability that C is equal to I given X. So this is the conditional probability, can be written as this joint probability divided by this probability of X. But we know that X has this mixture distribution, right? You've already calculated that. So this joint probability in the numerator using the multiplicative rule can be split in this way. So probability that we have the ith cluster or X is an ith cluster is X given C is equal to I times probability C is equal to I. But X given C is equal to I, we know that the density of that is just f of I, right? Because if X is an ith cluster, its density is just Fi. Times probability of C is equal to I is just Pi. So the conditional probability is given by this particular formula. F mix, the mixture distribution, just involves these pKs and fKs again. So if I know the k, if I know all the pKs, if I know all the fKs, I can calculate these probabilities, okay? And once I know the probabilities, then I can easily do the clustering. So the idea here is to, behind making all of these probability assumptions, is to calculate these conditional probabilities, right? That is the goal here. Okay, but there's another problem, right? We don't really know any of these terms, right? We do not know any of these. We just have a bunch of data set. We don't know how many clusters there are. We don't know what distributions they come from. Even if we did know, say everything comes from a normal distribution, we don't know the means, we don't know the standard deviations or the variances. We know nothing, right? So how do we determine all of these many unknowns just from data set. So you can see how this is much more complicated than k-means clustering. In k-means clustering, we only had to decide how many clusters there are, and the algorithm took care of everything. Here we have to decide how many clusters, what distributions. Then each distribution has its own set of parameters. So we have to we have to take a lot more efforts here. So we need to estimate all of these parameters from the data set. So we will be using like a principle of likelihood, or the maximum likelihood. So the idea is we build this likelihood function from the data set, and we estimate parameters such that in order to maximize this likelihood function. So if you remember, to maximize something, you differentiate with, so if I want to maximize this likelihood with respect to some parameter called theta, right? So say I have this likelihood function x, it's a function of this parameter theta, and so basically I'm going to differentiate this with respect to theta equate to 0, right? And solve for it, right? So I'll get into more of these details later on, but I just want to give you an overall idea of what is going on here. So many times the equations that will result from this likelihood estimation cannot be solved directly. So we'll see a few examples where it's easy to solve these equations, and we'll try to see some examples where it is not so easy. So in these cases, we'll use the EM algorithm. Okay, so there are softwares that directly execute this algorithm. If time permits, we'll take a little bit of a peek or a little bit of a look inside this algorithm. So in the next video, we'll look a little bit, we'll take a look at multivariate normal distribution, because we will assume that all of these densities, we'll assume that all of the clusters are generated from multivariate normal distribution. And then in that context, we'll use the maximum or this likelihood principle to set up our objective function to obtain the parameters.